Hi folks, Mr. Long here with another screencast about the fundamental theorem of calculus. And in this screencast, we're going to develop a little bit more about the idea of the fundamental theorem in more algebraic form. So we have two things going on here. We have a rate graph right here, okay, and then we have to think about the accumulation of rate. Okay, so again, I apologize for always using the snowfall graph, but it's a really nice way to connect accumulation to real life. So as snow falls, it literally accumulates on the ground. We take the snowfall rate, which is 3 centimeters per hour, and that means that every hour 3 centimeters of snow will accumulate. So the snow will get deeper and deeper and deeper, okay, by 3 centimeters every hour. So a snowfall rate of 3 centimeters per hour gives us 0. So if I was to put it on the graph, on a different graph rather, it would have 0, and then after 1 hour, 3 centimeters, after 2 hours, 6 centimeters, 9 centimeters, and so on, right? That's what the way things would accumulate, okay? So it would be 3, 6, 9, 12, and so on. So that's the accumulation function. So, and we can also call that the original function, if you will. So, and then in terms of naming functions, what we do is we name the rate function. If we name the rate function f of x, accumulation is capital F. Similarly, if we name, this is a special calculus thing, if we name the rate function as f, it's called f prime of x, then the accumulation function is named just f of x, okay? Just f of x. Oops, that should be there. Okay, so if rate is small f, accumulation is big F. If rate is f prime, accumulation is f. Okay, these two functions are very related. Okay, so let's go through this. So this time, remember we talked in our last few screencasts and our lessons at school about the notion that the rate function and the accumulation function don't actually tell us how deep the snow was, right? It just tells us how much fell on the ground. Well, what if we introduce this to our situation? So now, again, hours, this is being measured in hours after 8 a.m. So this would be 8 a.m., 9 a.m., 10, 11, 12, and 1 p.m., right? Hours after 8 a.m. So if there were 40 centimeters of snow on the ground at 10 a.m., how deep was the snow at 8 a.m.? Okay, so we know that if I'm going to get how deep the snow is at 8 a.m. and I happen to know the depth at 10 a.m., so there's 10 a.m. right there, okay, and I need to find the depth of snow at 8 a.m., right? I'm going to be looking at 0 hours after 8. So that means I need to look at this area. But if I look at it, where am I starting at? I'm starting at 10 a.m., right? Because that's the information I have. I have 40 centimeters of snow at 10 a.m. And how deep is the snow at 8 a.m.? And this is some intuition I think would help. So if we think about how deep the snow is at 8 a.m., and we think about how deep the snow is at 10 a.m., I think we know if the snow's falling that the snow is deeper at 10 a.m. than 8 a.m. So if I look back in time from 10 a.m. to 8 a.m., which I have to do in this situation, will there be more or less snow? There'll be less snow. And the reason for that mathematically is that our delta x is 2 to 0. I'm changing from 2 hours to 0 hours. So it's 2 hours in the past. Okay, so I know that I have, calculation-wise, and I'm going to call f at t, by the way, is the snowfall rate. So that makes big F at t the accumulation function. Oh, and what will the units be on big F of t? We've learned about this as well. So accumulation is always delta y times delta x, or centimeters per hour times hours. So that will just have units of centimeters. Okay, centimeters. Okay, so So the snow is 40 centimeters deep at 10 a.m. How deep is the snow at 8 a.m.? Okay, so here's what I know. I know the snow is 40 centimeters deep. Okay, and then I'm going to add on the accumulation from x equals 2, which is 10 a.m., to x equals 0, right? I have to, because I know 10, so I'm working backwards to 8 a.m. And then I'm going to put f of t dt, because it's not x, it's t. Okay, so I have that. What do I know about that? Well, I know that that's going to be, 40 centimeters of snow on the ground at 10 a.m. And then I've got to do delta y, delta x. That's my delta y. That's my delta x, right? dt is like, or delta time. So in this case, f of t is the y value. The y value is y equals 3 centimeters per hour of snow. So that's going to be 3 centimeters per hour. That's a positive, right? Because we always measure from the x-axis to the function value. And I need to multiply that by dt, which is delta x. And delta x is going to be negative because I'm going from 10 a.m. back to 8 a.m. So that's going to be negative 2 hours. So unit-wise, those units divide out, and I'm left with 40 plus 3 times negative 2. Well, what's 3 times negative 2? Negative 6. 40 minus 6 is 34 centimeters of snow. Okay, 34 centimeters of snow. Okay, so if you think about it, it's almost like y equals mx plus b in a sort of way. I have an initial value, and then this is what it's changing by, right? It's not quite the same, but it's close. Okay, it's close. Okay, so I have an initial value, I add the change, and that gives me an ending value. Okay, it's that simple. Let's look now if I go to 1 p.m. Okay, I got to go to 1 p.m. So again, what information do I know? I know at 10 a.m., which is x equals 2, I know the depth is 40 centimeters. Okay, the depth is 40 centimeters. And then what I do is I can move now, and I can figure out how much snow accumulated from 10 a.m. to 1 p.m., which is at t or x equals 5 or t equals 5. Okay, so I need to work with this area here. Okay, my delta y is going to be 3 centimeters per hour. Delta x goes from 2 to 5. So my delta x, which is delta time, is 1, 2, 3 hours. Okay, 3 hours. So what do I do now? Well, I know that it's going to start at 40 centimeters. I'm going to add the integral from 2 to 5 hours, f of t dt, so y value, x value, and that will equal the depth of snow after 5 hours. Okay, so 40 centimeters is what we started with, and what's the accumulation? The accumulation is, well, delta y here is 3, 2 to 5, right? 5 minus 2. You can see that really clearly. 5 minus 2 is 3 centimeters per hour. And then we're going to multiply that by dt, which is, in this case, dx, which is, sorry, they're both 3 in this case. My apologies. So 3 centimeters per hour is not the 5 minus 2. The 3 centimeters per hour is the y value. The dt, delta t or delta x, is 5 minus 2. All right, I should have put that there, 5 minus 2 hours. Okay, that's gone, that's gone. And then I'm left with 40 plus, well, that's worth 3. 3 times 3 is 9. So that gives me 49 centimeters of snow at 8 a.m. So now what we've done is we've taken accumulation, rate, turn it into accumulation, and then by adding just 1 point, 40 centimeters, we know actually how deep the snow is. Okay, we add an initial value. Except the initial value here can be at any time. It's not just at x equals 0. It's not a y-intercept. It's an initial value. Okay, and everything's relative to that. Okay, so we know 40 centimeters at 10 a.m., and I can go back in time to get depths of snow on the ground, and I can go forwards. And it's something as simple as a person went out at the, they started measuring the snowfall rate at 8 a.m. So they've got some sort of instrument that measures how fast it's snowing, how hard it's snowing. And then at 10 a.m. they run out and they measure how deep the snow is on their front lawn. Then they come back inside and they have an instrument that measures the rate of snowfall the rest of the time as well. And they use that rate in combination with that depth at 10 a.m. of 40 centimeters to get depths at any other time. Okay, so it's using rate with one value of depth to get depths at any time. Okay, so hopefully that helped. Actually, you know what I'm going to do now is I will just, why don't I just add a page here and formalize this. Okay, I'm just going to formalize this. So if we looked at that last example, okay, this last example, 3 centimeters per hour, t equals 2, t equals 5. And we wanted to get the depth of snow at t equals 5, okay? By the way, that's f at t. So if f at t, excuse me, is the rate function, big F at t is the accumulation function. So when I'm asking for depth of snow is related to big F of t, right? So what did I want to figure out? I wanted the depth at 5 hours. So I wanted to know f at 5. And what piece of information did I start with? I started with the depth at 2 hours. Well, that means that f at 2 was that 40 centimeters. Okay, that's what I knew. So f at 5 equaled f at 2, which is 40 centimeters, plus the accumulation from 2 hours to 5 hours, f of t dt. So now, though, again, what does that 40 centimeters represent? That 40 centimeters represents f at 2. So f at 5, the depth of snow at 5 hours, equals the depth, the known depth at 2 hours, plus accumulation from 2 to 5, f of t dt. That, folks, is the most useful form of the fundamental theorem of calculus, because this right here will be what's known. So that's a known value on the original, or accumulation. So in our case, that was our 40 centimeters of snow on the ground. This right here is accumulation of rate. And f at 2 is, that's what you want to figure out. So we can generalize this. And we can generalize this. We can say that f at b equals f at some value a. Oh, because notice. 5, 2, 5, 2. So if this is b and this is a, our integral will be plus the accumulation from, so right here, that's 2 and that's 2. So that's a, and this will be a. This will be b, and this is going to be f at x dx, or t, it doesn't matter. Okay, so that, folks, is our generalized fundamental theorem of calculus part. And there's different ways to write it, of course, because you can isolate this, you can isolate this, you can isolate this. There's 3 terms there, you can isolate any one of them. So there's 3 ways you can represent that. Okay, so again, that is our generalized form for the fundamental theorem of calculus. A known value on the original function plus the accumulation from x equals a to x equals b gives us the y value on the original function at x equals b. Okay? This is a y value on the original. This is accumulation of the rate function f at x, and that gives us f at b. Okay? We would also call this the net change. So this is how much the y value changes on the original function from x equals a to x equals b. There's many, many ways to think about that. All of them extremely important to understand. Okay? People that get this, and I'll tell you, I did not understand this very well when even at the end of first year university. I don't think I really understood this till second year university. Hopefully you'll get a sense of it conceptually this year. Okay. All right. So that's this screencast for now. You're going to practice a few questions now, and then we will go from there.